Alright, time for another DraftScience video presentation. Dun, 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 dun. Anyway, I was provided a link by a long-time viewer. Not anything like you, no doubt. But anyway, so this is just cornstarch mixed with water. And you may have seen these. Of course, everything's turned into some sort of entertainment television, so they make giant tanks of it and people slide across it and do all kinds of other stuff, and, the interesting physics gets lost. So anyway, the idea is this is just a demonstration of, say, the opposite of clay. So clay has a bias for things that are fast, and cornstarch and water has a huge bias for things that are slow. So, I don't know if it's probably not worth playing the video, but we'll play the ending of it anyway.
Solids and liquids, fine particles. They behave unlike anything you might expect.
Right, so if you vibrate it quickly, it gets all kind of hard and it solidifies because the molecules end up, locking into each other. And if you relax it, it's like cactuses or something, then they, get individualized again because the little spines bang against each other. You can come up with all kinds of ways of why it locks more when it's moving and it locks less when it's not moving. So it just becomes stiffer, okay, the more activity there is. And and then you can sort of see it in the end here is where, it's just you get the giveaway, that obviously if probably, I can't say for sure, but if you did some ballistic test where you shot a bullet into it or you dropped a bowling ball, the bowling ball would go really deep and the bullet would, get stuck right in the surface, that kind of thing. So it would have the opposite effect of clay in that this test instrument, if you use this to catch energy, it's going to fool you because it'll use a lot of energy to solidify the substance, based on speed. And the thing that isn't going fast won't use any energy, won't have to interact with the fluid, and therefore will get a free ride. And so it'd be the opposite demonstration of how you really there's a science, okay, to all of this. And, it has to be well documented. You're going to do an experiment. You have to document, okay, that you've covered these bases so this doesn't have that tricky little bias in it. And that's not a complex argument. And all the physics should be able to recognize that it can't quote mine these experiments and say, oh, well, this experiment shows, this here we've distorted the controls a little bit and we can get an outcome. That's not fair, okay, is the simple thing to say. It's like when people put in, they start doing, whatever, two slit experiments and they start putting lenses in and they start manufacturing the outcome. And so that's probably what I'll get to in the second half of this video or later in the video. But anyway, we'll watch this.
Most things you would think
if he just pushes his finger in and is careful, doesn't go too fast, everything's real liquid, real easy, no friction, blah, blah, blah.
Really hard, I'm going to break it. This is a fluid normally, and if I hit it hard, it turns it into a solid.
I mean, you get it pretty clear that obviously the fast thing, huge bias against it. Okay, so if you use this stuff to test how far something goes, it's going to really tell you that somehow heavy things fast things don't have any energy. Bullets, they won't go very deep, and bowling balls will go forever. Because they're slow. And so just pointing it out that this is all part of this argument that, and apparently, this shouldn't even be something has to be argued about with reasonable people. They should know that you have to do experiments carefully to get results that mean anything. And, I shouldn't even everybody should be able to raise their hand and say, yes, let's do the experiment as accurately and as controlled and as precisely as possible. Everybody should put their hand up and say, yeah, that's what I vote for. Let's not draw conclusions based on, it seems like, let's not do it, it's easier to do it this way, let's not slide things and pretend they're rolling when they're not rolling, it's just, this shouldn't be an argument. Everybody who loves science should love it done well, and open. Let's see it all. You know, like even LIGO, you know, it should be right on the first page of them talking about the experiment and pointing out, yeah, we're bouncing the light in a mirror 1,600 times. Yeah, we're not just going to the end and then back again. Okay, the whole mile thing wasn't nearly enough. 2 miles wasn't enough. You know, to do the experiment, we really need, 14, 8 or 900 miles of tube, and we just can't make that big a tube, so we're going to just bounce it back and forth and pretend it doesn't matter. That should be sort of, when you understand the experiment, you should understand that that's in there. Because it's a huge piece of information that could create some doubt about the credibility of the experiment. Is this really what they say it is? Alright, so that's probably enough for this moment, and I'll switch to another video and such. Alright, I switched to a comment instead. Okay, so Matter Dirk says, what we could do is agree on the equipment used for any experiment. Well, again, I sort of made videos saying this exact thing, in the sense that I'm willing to pay somebody to do these experiments well. And Stephen Bro thinks I owe him the money now, because he thinks he did them well. And, I described metal tracks. I described you have to do it so you eliminate friction and eliminate all the little things that could get in the way of getting accurate results. And he just ignored all that part and pretended he can just, tie some crap together and glue some stuff together, and there, we're done. We've, done our scientific thing, and it's not very good science. So even this premise that we are going to do the experiments at home, is pretty unrealistic. There's air tracks for a reason, because, it works, it helps. It gets the noise out of the experiment, okay? You're eliminating the problems that would occur with all these other methods. And, they have an air track in, like, Harvard that is brilliant, in the sense that it's really good. Okay, I mean, it's like no friction at all. They can keep the thing bouncing back and forth, for an hour or something. It's, really good. Anyway, what we could do is agree on the equipment used for any experiment. Yes, that has to be the premise, especially for me to pay for an experiment, right? So if you're going to volunteer to create this experiment, which I would like somebody to do, just this simple experiment, launch 2, masses, and have them, equally blighted by friction, one half the mass, one double the mass, and launch them with the same amount of force, and then just catch them with another device that honestly catches the momentum, that is, measures it consistently. Now, springs are pretty good. They're a little bit, disproportional, but they'll tell you they'll make very good relative comparison. So, I mean, the limitation of a spring is that you hit it with 100 joules. Let's say this is its relaxed position. Okay, you hit it with 100 joules, it compresses this much. Okay, you hit it with 200, it doesn't compress another half, it just compresses, say, here, and then, it doesn't do a nice straight line. It's more, instead of being a perfect this, it's more like a this, kind of line. But otherwise, it's really good at measuring, doing relative comparisons. It'll always give you good results. It doesn't have a huge bias for how fast you move into it. Now, if you shoot a bullet into some springs, they're just going to shatter because they can't absorb the energy quickly enough, and so they'll break. So it has its limitations, and so you have to understand that you're within the tolerances, I use that word, tolerances, you're within the tolerance of the physical device, and you can be sure of that. You can test it and be pretty certain that you're not messing up. But it is something you have to do. It's not unimportant detail. Anyway, all right, used for any experiments, so the audience can match the materials at home. Now, see, that's the part where I say just totally fail. I don't need to do the experiment. I just need somebody else to do it honestly, okay, where they actually show what they did. Well, why do I need to do it? I don't need to do it. If somebody does it well once, then why don't we just use that forever and just say, yeah, there's the experiment. You know, why do we have to do it at home? You know, that's, you know. And again, I'd use the example with all of science's money and resources, the fact that they've never redone the Eddington experiment. I mean, one of the most important experiments verifying Einstein's theory, and yet it's never been redone with better technology, and certainly never done from space where there's 400 times better resolution. So apparently this is a conversation for which there is great disagreement. You know, even though all these, you would assume that all the scientists have been, you know, they read the same, you know, run scientist run book, you know, the run spot run kind of, you know, one of the key things to science is, yes, doing this thing, making the experiment credible by redoing it. This is one of their, you know, this is one of these sacred pinnacles of the, you know, the whole thing is this is how science works. And yet apparently people will argue that no, that's not how it's supposed to work. You know, we don't have to do any of that stuff when it's verifying our beliefs. We don't have to verify. We don't even have to do the experiment. You know, so they'll talk about single photon experiments, and they'll talk about detector experiments and all kinds of experiments they never even did, and they'll claim the outcome. You know, but you're never going to see the actual experiment done in some clinically careful way where any of this was proven. Now, I just showed that. I showed you another guy doing like the Veritasium thing and saying he's doing single photons and he's using a microscope and all that stuff. And I did leave a comment on his video pointing out I did a response video, and it has disappeared. So I guess he's not going to respond to any of those critiques. But you know, the truth is you know, he's overtly in the video making excuses for, I have to do the video in a shorter and shorter period of time because I have to turn up the camera, you know, and I can't make it work, you know, unless I find an excuse to shove more photons into the experiment at you know, per second. And that's the simple truth, and they just won't say the simple truth, which it doesn't work. Okay, you know, unless I really do challenge the fact of whether there is a single photon in the experiment. If I'm sure there's no photon, you know, it's only one photon at a time, that is, I take a long time to do the experiment, it doesn't work. And that's the simple truth they're not telling you. But anyway, so, but doing this stuff at home, like I said, well, that's the wrong approach. That's how the science goes bad, is you have a bunch of amateurs farting around. That's how this whole MV squared thing got off the ground. Is these weren't really great scientists, okay? They didn't sit there and do the fair thing, you know, where you don't sit there and, you know, use cornstarch, use this, use that, use all kinds of things that verify your results and completely never show the results when you did it in some other way, when you used a spring, and not showing those results. That's not good science, and that's entirely the science that got this stupid thing off the ground, was quote mining the evidence, a willful, deliberate effort, you know, to pretend the alternative evidence doesn't exist and only this evidence exists. And clearly Feynman does this too, you know, presuming like they've already done, they thought about all the possibilities and none of them work, and so therefore you have to believe us, because we thought of everything else and none of it worked. You know, I mean, those kind of statements are so unscientific. But anyway, let's be vigorous. Yes, that's a nice ambiguous statement. I mean, how about let's be honest, let's have integrity. Okay, let's not cheat the historical truth. Let's not cheat, you know, the physical facts. I mean, the physical facts are Stephen Bro's experiments sucked. Okay, I mean, they were documented horribly. He put this crappy music on it, these silly images all over it. I mean, it was just complete crap. Okay, anyway, so he says, in Stephen's video, I do see the thing that hits the coins. Yes, we could all see the thing hitting the coins. The problem is that he didn't tell us what he was using or how he was using it or anything. We didn't see the mechanism, didn't see that it produces consistent results, didn't have any guarantee that this was at all what he implied it to be, which was a mechanism for producing half the velocity. Didn't show that happening. is on a slight angle, so I assume it is on a pivot, as you said. Yeah, yeah. But you're saying it in hindsight, right? After I've already told you, and now you can see it, right? But would you guess before I told you it was a pivot, that was a lever? Is that your first impression? Did you just watch the video and go, "Oh yeah, there he's using a lever"? I don't think he did, because it took me 2 or 3 times watching the video before it occurred to me. I could be wrong. Stephen could clarify. Yeah, well, the point is yes, he has clarified that's what he used, but he hasn't clarified that he tested it in any way whatsoever, or that he demonstrated through some kind of evidence that he did any work to figure out whether his lever was actually, calibrated properly to produce the required outcome. That we have some reason to be assured that every time he did whatever he did, that he was in fact doing what he claimed to be doing, which is giving one object half the velocity. But thanks for the comment. At least you're verifying that it is subject to some doubt. You get it, that, hey, he could have done that better. A lot better. Okay. So this other guy talks about bowling balls. I guess I might as well throw it in. Gary, in Boston, we have candle pin bowling. I think that's just Canadian bowling, right? I mean, straight pins and little ball. And you say the ball is lighter than a regular bowling ball. Well, it doesn't have holes in it either, right? So it's a cannonball you're throwing at pins. Probably. I don't know. Maybe there's some other kind of bowling. And here's the kicker. The scores do not tend to be higher. Again, anybody with any kind of cognitive skills, I think, can understand that it casts at minimum doubt. So when science says, okay, the 8-pound ball creates twice as much kinetic energy, okay, that you'll have, throwing it with the same amount of muscle effort will produce twice as much energy. Okay, that's overtly what their theory says. It makes no sense on its face, because you're saying the same energy is throwing the ball. How the fuck could it possibly have twice as much energy? And how the fuck did somehow, if I'm throwing the heavy ball, somehow half the energy doesn't get to the ball? Like, it's the same exact arm motion, right? You're doing the same thing. You're just doing it a little faster for the 8-pound ball, right? So you're doing it twice as fast for the 8-pound ball. I'm doing this versus this, right? This versus this. And somehow when I do this, I lose half the energy. Half the energy's gone. I mean, what? Well, how? I didn't notice, like I said, I didn't notice that all my fingers broke or something. I didn't notice that all these problems, I had all these problems ejecting the ball, with the energy, that somehow there was a 50% of the energy, which is a lot of energy, right? Throwing a 16-pound ball down an alley is kind of a lot of energy. And you're saying half of its energy was somehow dissipated as heat or something. Like somehow, I caught fire. Because I threw a 16-pound ball, my elbow made too much friction and it, melted. What's the theory? It doesn't make any sense. So, I mean, it's on its face silly. Is there any other word for it? I mean, realistically, all you trolls, you really think I'm intuitively or reasonably or in any way I'm somehow dysfunctioning because I tend to doubt that theory. I can't see any way it can possibly make sense. I throw the ball with the same force, and yet one ball has twice as much energy as the other. How the hell could that be possible? I mean, how could it have extra energy when I threw it with the same muscles and the same body and the same calories? I mean, I used as much of effort in throwing, yes, I throw the 16-pound ball slower because it's heavier. But I'm using the same energy, so how can it make any sense? You really think that makes sense? You really think so? You really think? I just don't know how to make. I don't know why you're making these arguments and being so hostile when somebody just questions something that's so overtly nonsensical. And then you have, on top of the That's not my life experience. That's not how I see the world. And then you see the fact that every professional bowler, for some dopey reason, is not taking advantage of this huge, beneficial and more energy he's going to get by using a lighter ball. Just going to the 12-pound ball, he's gaining 50% more pins. I mean, just going to 12 pounds from 16 to 12, he gains 50% more pin power, more pin knocking down power, more joules of energy. Well, why wouldn't he do that? I mean, how is it possible for him to fail to be able to realize any of that? No professional has ever figured out how to throw a 12-pound ball instead of a 16-pound ball when it has twice as much, 50% more energy? Could somebody please give me the reasoning? Just explain, just write in a comment how I'm unreasonable, because I don't think that's what happens in the real world. I don't think that energy has anything to do with reality. That I think your measurements, your predictions, science says, I think science isn't saying anything rational. Explain to me why I'm being unreasonable, because you have zero evidence for it. You can't show me the 8-pound ball knocking down more pins. It's a fact. You can't show me it happening, even though it's supposed to knock down twice as many, okay? Not just a few, twice as many. And why can't you show me it doing that? Can you answer me? I mean, can you provide some reason why I'm an asshole because I tend to doubt the science says theory that the 8-pound ball has twice as much energy, joules, capacity to create movement and heat? It has twice as much? I won't be redundant, but there has been no such comment. All there has been is an insults to my integrity. There has been no explanation for why it is unreasonable, why the evidence is so overwhelming there's no way you can doubt. All they keep saying is, well, our derivative says so. And I showed the derivative. I mean, it's a dot product. It's supposed to be used just to tell you which direction something is. You do the math with a dot product. The dot product's really not supposed to be part of the math. It's just a directional orientation. So you're tracking the energy here, or the real thing here, and the dot product is sort of just an unreal representation of which way it's pointing. You're not really supposed to consider the pointing vector to be an actual new vector that you multiply against the other vector. It's not really supposed to be part of the actual end product. It's supposed to just tell you what direction the end product went. So anyway, so what this is just crazy, okay, that this goes on and on and on. All right, so since I'm on comments, I might as well do this other guy. I deleted most of his comments, but they're just trash. I left a couple just because they're worth they're worth saying, what are you talking about? Okay, I think it's like this. You're in space and you want to push off at 2 miles an hour. Is it easier to do this by throwing 10 baseballs, one after another, or a single bowling ball? Well, frankly, it shouldn't make any difference. Okay, I mean, going this way, doing this, takes as much energy as doing that. Okay, so if I do it all at once, or I do it this way, it really isn't going to be much difference. It depends on how much friction there is in the pivot and all that kind of stuff, but the fact is you're really supposed to be using the same amount of joules per launch. So whether you shoot, like if you had your rocket engine and you turn it on and off, it's not going to make any difference. You shoot the thrust in little bursts, or you shoot it in one long burst, it's still the same amount of thrust, so it doesn't make any difference at all. If the little bits are going the same speed, you throw the 10-pound thing 90 miles an hour all at once, or you throw it in 1-pound increments 90 miles an hour, it's the same thing scientifically, frankly. So he's presuming this isn't true. So it's his assumption that it somehow makes a difference how a rocket ship throws its thrust out. So if it does it in pulses, like a pulse laser or something, somehow it doesn't work. Yeah, it does work just as well. All right. In both cases, the momentum is the same. Okay, so you've got that part right. It took the same energy. You've released the same amount of pieces going at a velocity. So you've used the same energy. There's the same amount of pancakes, coming out. You had to use the same amount of flour, so to speak. In both cases, the momentum is the same, but one requires more energy. Why? Explain. You won't do that though, so there's no point in me asking, right? Because you won't explain. Well, you can't now because you're blocked for being a troll. A real scientific engineer would need the energy equation just as much as the momentum one. So clearly NASA scientists have said pretty overtly, we just use Newton. Okay, that's how we land on the moon. Newton. Okay, and Newton does mean MV. Newton doesn't mean MV squared, 1/2 MV squared. Newton doesn't mean Leibniz. All right, so, and no one's really shown me how when they were landing the lunar module on the moon that they were calculating how much thrust they needed based on the 1/2 MV squared. So we have absolutely no evidence that any navigation in space has ever taken place using MV squared, 1/2 MV squared. So you can say it, okay, but you don't have any evidence of it. So if you want to show me the evidence where they actually did those calculations using MV squared, because I can show you web pages where they clearly give two different numbers. The Newtonian physics gives one number, the MV squared number gives a different number for how long you have your engines on. Okay, and that's huge, right? You know that's going to make a huge difference to what happens is how long you have the engine running. So if you're calculating how much energy is leaving and how much energy you're getting in an equal and opposite reaction, and you're calculating by MV squared, you're going to get a very different answer than MV. And you should at least concede that one of them has to be right and one of them has to be wrong. And NASA either used one or it used the other. But it can't use both because they're completely contradictory answers. One says 10 minutes, one says 7.7 minutes or something. I mean, they're completely different answers. All right. He said Irwin's experiment, Lewin's, is different than the one Piro's talking about. Well, the fact is Piro wasn't talking about an experiment. So this is the part. I didn't understand where he was going. He didn't premise his argument with, I'm just going to talk about how the spring imposes the energy. I'm not going to talk about what energy it has after it leaves the spring. Okay, so that's the big confusion of what Piro did, is he was again way off the subject. So what he was showing was that springs, see, if I don't put any weight on a spring, I better do this. All right, so I don't put anything in front of a spring. So I take a spring and I compress it, all right? And then I let it, so it's compressed and I let it go. This spring will move at a maximum velocity. That is the velocity of nothing to push. So it has no mass, extra mass to move. So it moves at its maximum velocity. And that's part of what will be its spring constant. Okay, is what's the maximum velocity of the spring. Then when I put a weight on it, okay, so now it has a weight on it. Now what's going to decide the velocity of the spring is how big is the weight. Okay, the more massive the object, the slower, okay, the spring can push. And so this object, when the spring reaches its maximum, it gives back all its energy, goes to its maximum distance. This velocity is completely dictated by the size of the mass. All right, so I make the mass half as light, the velocity will be twice as much. Okay, and that's just the way that's the way it'll work every time. But the idea is that this spring regulates how quickly the energy can be transferred based on how heavy the object is. So the heavy object takes longer because it has to move slower. The lighter the object, the faster the spring can move. Now the catch is you can't put so light an object. If this object is lighter than say the spring's mass, then it won't be. It'll leave at the same speed. It'll achieve the same speed as the spring very quickly. So before the spring completely expands, this object will have already left at that velocity. So it'll gain the velocity before the spring is finished. Therefore, it can't get the extra energy. So if I put a very light object on, I won't get the energy from the spring. I'll just get partial energy from the spring. So only part of the energy of the spring will go into the object, and the spring will just go out the rest of the way and then back the other way, which means it's going to push this way eventually. But anyway, so if I don't put a heavy enough object on, then I'll imbalance the spring. But it has to be a very light object, obviously. So that's not something we're in jeopardy of doing in any of these experiments. But anyway, so Piro was just charting, okay, how the spring, when it first starts, it has to push slowly, right? It can't go the maximum speed and then slow down. So it starts off pushing slow, then faster, and faster as it expands. But it has a limit to its expansion speed. So it tails off to nothing. It tails off to a flat line because, yes, it has a maximum speed and can't go any faster. It can't move any further out because it used up all its energy. So the speed of the spring's expansion is, one of these curved lines. So he wasn't talking about the thing leaving velocity-wise. He wasn't talking about their momentum. He was just talking about how fast the spring moves, which doesn't really say, how the spring imposes the energy has nothing to do with what we are going to know is the energy. We can measure the velocity of the objects after they leave, so we don't need this information about how the spring imposes the energy. The important fact is how much energy does it have? How many joules does the thing have when it leaves? That's the thing under debate. All right. So that was obviously another bit of confusing mush where somebody's making a science argument and they really just don't give you any of the details of what exactly they were talking about. And so they lead you astray, not by any intention, but clearly by the fact that he's not making it clear that he's measuring the energy the spring is producing, which doesn't have anything to do with the fact that we know the two things don't have different momentum. So we know if we compress the spring the same amount, the spring can only produce that amount of energy. And only if we do something silly, like put a brick wall in front of the spring or put a feather in front of the spring, are the results going to be not what we can predict. All right, let's see. So then he says, is different than Piro's talking about. So Piro didn't talk about an experiment, okay? He just talked about moving a spring. So he didn't talk about anything moving away from the spring. None of this subject, again, totally off the subject of what happens when an object leaves the spring. And what are the facts about what happens to the object as it leaves the spring. He demonstrated nothing about that. Okay. So, and understand the Professor Lewin video is in a context where, he's done the experiment with two, I showed you the whole experiment. I showed in the clip part of the experiment. But you get there's no way around what the conclusion is, is that one side of the experiment doesn't care what's on the other side, and it's just a fact. That you're going to get the same result this way no matter what's over here. Over here can be 10 pounds, it could be 100 pounds, it could be 1,000,000 pounds, and what's going that way is still going to be 100 joules. 100 joules, 100 joules, 100 joules. All right. You have to set the spring against an immobile object. So again, just absolutely no proof for that. So you have no evidence for your assertion, you're just asserting it as a fact. And you're providing zero evidence, just zero, zero, zero. I would argue that's incorrect. Okay, and I would say that Professor Lewin's video gives you every indication of why it's incorrect, because the result is is that it doesn't matter whether I doubled the mass. I put twice as much mass on one side, and I didn't change this side at all. Nothing. No change this way. So I put twice as much mass, no change this way. Alright. Then you get different momentums. Says you. The same compression of a spring can never produce different momentums. And it can only do it, like I said, if you put something extremely light on the spring, then you'll get a different momentum. But that's the only possible way to screw it up. There's no other way to mess it up, okay? The spring always produces the same energy for the same compression. So this is just, like, again, your assertion. And you do it with capital letters. Where's your evidence? Yeah, and I'm an asshole because I say, where's your evidence? You don't have any evidence. You have no evidence, zero evidence. No one's provided me a single indication of any evidence whatsoever to support your notion of some sort of different momentum. And you heard Professor Lewin overtly say in the video, momentum is always conserved. So, again, where's your evidence? Oh, that's right, you don't have any. Okay. In Lewin's experiment, the position in space where the two springs are touching changes. The position in space where the two objects are touching changes. It doesn't matter where they are in space. He's just measuring their speed. That is how fast they pass a thing. So it doesn't matter whether they're here or here or here. They get to the thing, they turn the timer on, and then they turn the timer off. So it doesn't matter when they get there. It can only make hundredths of a millisecond of a difference. If you measure the velocity further away, it'll be a little tiny bit slower. But that's all, a little tiny bit. Okay, so another assertion that has no merit. None at all. The position in space where the two springs are touching changes. There's not two springs, there's one bow spring. It's one piece of metal being bent. Okay, so it's a piece of metal that's a spring, and you're compressing it like a bow. Okay, so the force applied is the same, but the work done is different. So there's absolutely no point in anybody ever saying the force is the same and the work is different. It's just babble. There's no way for you to defend nonsense like that. You can't have the same force and different work. You can't do it. It's impossible. Okay, if you position the spring, I didn't read this one, it's so hilarious, against an immovable object, the force is the same. So again, we already demonstrated it's already the same. I put it twice as heavy, I put it 4 times as heavy, I put it 10 times as heavy. It just isn't going to matter. What's going that way is always going to be 100 joules. Always. Okay, so you're making an assertion and you have no evidence for it. You're just an arrogant troll who just sits there and talks science, but you don't walk any. You're not going to put up anything. You're not going to prove anything. You're not going to demonstrate anything. You're just going to tell people, believe me, because I'm a troll. Okay. If you position the spring against a movable object, the force is the same and the distance applied is the same. So again, what does that even? It doesn't even mean anything. The argument is that the spring produces a certain amount of energy, and it will cause the thing to move at a certain speed based on its weight, and that you can't change how much momentum the spring can produce. And it's almost an insane assertion you're making. I mean, it's an insane assertion in the sense you have zero. There's just no evidence anywhere that you can produce these different momentums. You have zero evidence for this. Zero. I mean, how many times do I have to say there's zero evidence? Could you show me one thing, one single shred of an evidence? You're showing me no evidence and then making claims that are extraordinary, frankly. Extraordinary claims with no evidence. Alright, the force is the same and the distance applied is the same, so the work done is the same. What does that even mean? And fine, I'm saying what you can't argue is that they have the same velocity. So again, we're right back to the same argument. Okay, we're saying the bowlers are pushing the bowling ball as hard as they can, let's say. They're throwing it as hard as they can, and you're saying there's a huge difference in how much momentum it has. If I'm throwing a shot put as hard as I can, or I'm throwing a baseball as hard as I can, you're saying somehow I'm applying unequal forces. We haven't demonstrated that there's unequal amounts of force in the objects. And the clear fact is the baseball player can throw the baseball 90 miles an hour. He can throw it pretty fucking fast. So, and if I put a cannonball in his hand, he's not going to throw it nearly as fast, and you know that. But he can do just as much work on the ball, okay, trying to throw it. And the simple fact is that he can throw them with the same amount of energy. So we're already conceding. Let's throw them with the same amount of energy, one that's twice as heavy, one that's twice as light. Okay, and we already know what the outcome's going to be, is one's going to be going twice as fast as the other. Because as Professor Lewin stated, momentum has to be conserved. You can't change those rules. Too stupid. Anyway, so the work done is the same, but the momentum becomes greater for the non-massive object, for the more massive object. So this doesn't even make any sense either. The momentum becomes greater for the more massive the object, when their theory says exactly the opposite. There's more energy in the faster, lighter object, not the more massive object. So again, how does it make any sense? So they're saying that the heavy bowling ball has more momentum, whatever the fuck that is, right? I mean, what the fuck's momentum if it isn't some kind of energy? So they're saying it's like anti-energy. So they're like, momentum is like anti-energy. So whenever kinetic energy goes up, momentum goes down because it's anti-energy. So that's how you're supposed to understand momentum. So when somebody tells you something has a lot of momentum, that means it's going invisible. That means it's getting lighter and lighter or something, because it's anti-energy. It can't make any sense. So again, these people just deny the history. Clearly the MV square was a replacement for MV. It was saying momentum doesn't mean anything. It's giving you the wrong answer. Let's push it down and get rid of it. Let's replace it with MV squared. That's how this thing started. There's no other way to look at it. There's nothing compatible about the concept of kinetic energy and momentum as physical realities. You can't in any way put them into the same universe. They are anti to each other. They don't make any, the universe can't make any sense. You're saying 2 + 2 = 4, 2 + 2 = 7. You can't do that and be a rational being. So either pick one or pick the other. Overtly say momentum doesn't mean anything, or concede the truth that kinetic energy doesn't mean anything. One of them is the wrong answer, one of them is the right answer. There's just no point in this babble about, oh, the heavier object has more momentum. What the fuck is momentum if it isn't energy? If it's not energy, what the fuck is it? Come on. Too silly. Alright. So we will move on to some other bit of crap. Oh, there was a troll who said, I delete all the comments and all this kind of crap. Like I'm obligated to somehow endure their lies as premises to their arguments. No, I don't have to accept a lie as a premise to an argument. If you people can't resist constantly saying things that aren't true, completely unestablished by any evidence statements, why should they remain on a message board anywhere? Why should comments that are overtly inaccurate be sustained? And why should somebody have to, on every single one of them, type some comment saying, well, that's totally inaccurate, unproven, go through all the work of explaining why your assertion has zero credibility? Because frankly, it takes more words to explain why you're full of shit than it does for you to spew your shit. Cleaning up shit is more work than shitting shit. It's just a fact, and it's a fact I have a right to be rationally reactive to, in recognizing that, no, I'm not going to annotate every one of your retarded comments. So try to make not retarded comments, and then they won't get deleted. Anyway. It's just... Humans. Such shitty organism. Ugh. Fuck. Yeah. Yeah. So I was moving on. So I shall move on. Alright. So we're back to this, the real double slit experiment, which is a pretty bad title just because, yeah, he's doing this microscopically and all of that stuff. It's not exactly the real double slit experiment in those terms. And there really isn't any problem with light with us being able to do the double slit experiment in the way where we magnify it by projecting it, okay, and making it visual to our own naked eye. There's not some failure like to produce good enough results that way. Now, I'm not saying there aren't advantages and disadvantages, that you'll see something in this experiment you can't see in the other or anything like that, but this is more technically demanding in terms of your slits have to be perfect, and we never got to see what his slits actually look like. So the argument is when you're making very small etched slits in something and using chemicals to etch it, you can never get the stuff, you never get these edges perfect, and so they end up being rather jagged for the percentage of the slit. That is, the percentage of space is very small, okay? It's a very small absolute amount of space. So any irregularities become huge in terms of the percentage of the space they're incurring into. So when you're using a big slit and you have some jaggeds, it doesn't matter nearly as much because it's such a small percentage of the total distance, of what's going to affect the light going through. So anyway, that's one simple argument. The real point I wanted to make from this image is you can sort of see, okay, he's got a real round thing that has the slits in it, and then on top of that there appears to be two other layers of glass. Okay, so he's, if you look at it, it looks like there's three layers of glass. Okay, that he's got, well, I can't draw 3 layers of glass that way, so we won't bother doing it that way. So here's the little flat thing that has the slits in it, and then there's another piece of glass, and then there's another piece of glass. So there's 3 layers of glass. Now, as I've shown in previous videos, this is a known effect. When you put glass on top of glass, the problem is, this is how they even make beam splitters, is that you get what are called internal reflections. That is, the light starts bouncing in between these layers and comes out in different locations. So when you have 3 layers, you got even more of that happening, and that each one of those layers is going to create a bullseye pattern. Each layer is going to be creating a bullseye pattern, and the pattern is actually, again, it's projected through the glass, and so it's really a tiny pattern in its origin. Like the lines will be very close to each other, but when it's projected to the surface, the lines will look much thicker and bigger. And what's happening is the glass never sits perfectly. So it's always at a little bit of an angle, and that little bit of angle amplifies this effect. So each thing sits at a little bit of an angle, and you end up with these different lengths, and the different lengths end up being in phase and out of phase. So it's in phase here, and it's out of phase there, and it's in phase here again, and it's out of phase, and it's in phase. So depending on how it's tilted, you're going to get bar patterns. So he has a 2-slit experiment essentially on top of, okay, he's putting the light going into the slit experiment is being compromised by these layers of glass, and so he's essentially putting he's putting a bar pattern into the slits, and getting the byproduct. Well, you can see enough of that, yeah, so good enough. So it's part of the reason I would argue that he was getting a lot more bars than you would expect for the distance of the slits. Like this, the slits only had this was only 7 wavelengths of light, and theoretically, if you understand the math, you can't create path length differences that are a full wavelength from these 2 sources. With only 7 wavelengths of difference here, you can only get 7 notches here. Okay, there's only 7 places where there's a full wavelength of difference between these 2 lines. You can only get the number of wavelengths in here dictate how many possible locations there are where you can have a full wavelength of difference between the lines. if you have too little distance here, you can't have a lot of bars. You only get a lot of bars when there's a big distance from here to here. Like if you have 1,000 wavelengths of difference, then you can get 1,000 bars, here. And again, the viewing thing has to really be on an arced line. That's what the math is telling you where it will be in space on an arced line. That's what the math is predicting. The math isn't predicting out here and out here. It's predicting here, here, here. So that's even part of this whole the incomplete description they're giving you. They're not even acknowledging the fact that their math is saying this distance is always consistent. The distance from the surface to the location is always the same distance in the math. So obviously you can't go this further away distance and have it in your math as this distance. That's not the same. This distance isn't the same as this distance. So obviously the math isn't predicting here. The math is predicting here. These are, frankly, they're too obvious and too simple an observation, and there's really no good reason that all these physicists for all these years have been pretending this is what they're predicting when their math is clearly predicting this. I mean, this is something some physics student should have figured out a long time ago, that this whole conversation is sort of a distortion and a perversion because it really isn't connected to the truth. You can't predict here with the math unless you change this number, unless you put a longer L in the equation. You can't predict here. You have to predict here. Alright, so that's enough on that piece. Now we'll go to another video he did that I was also linked to by somebody else. I'd already seen it, but it was it's curious in the fact that it just brings up some more stuff about what I would argue is sort of he's conceding certain points. So in this video, he sort of in one place does concede that the surfaces are causing the effect, that the point sources are the surfaces, that the surfaces are the only place the light is being bent from. But at the same time, he's verifying a wave notion, that it's a wave coming out of a slit. So he's arguing for two different things. I mean, you can't have it both ways. If you understand that it's not an opening, like the water example, it's not this isn't what's happening in the experiment, okay? There's an opening and the water goes through the opening and creates a wave, okay? That's not what's happening, okay? And he's conceding that. So he's arguing for this, like the origin is here, when in fact he's conceding, no, this is where all of the fringe pattern comes from, is these surfaces. All right? And you can't have it both ways, right? I mean, this is 2 point sources, this is only 1 point source. So obviously we don't need to break the photon in two if what we're understanding is a photon goes through here and a photon goes through here, and these two photons go to the location and are matched in phase. Those are two different explanations entirely, requiring completely different physics. To make this photon magically pop into two is completely different than conceding, oh, possibly 2 photons went in and the 2 photons went to this location. I would argue that 2 photons didn't do that. These are pieces coming off of here in all directions. It's being scattered. And yes, some of the pieces end up at the same location, at the same phase, 50% of them, and 50% don't go back into phase. 50% are in phase, okay, the right distance from each other, and 50% end up not in phase. So no photon here, photon here. So you're throwing pieces and you're either matching the right distance between them or you're not matching. That's simple. Receivable signal, unreceivable signal. Good Morse code, broken Morse code. Lots of ways to analogize it. Alright, so I will go find the other video and such. Alright, should be back. I had a problem getting this video to play for whatever reason. So I'll just show the initial image. So I'm going to say this is sort of like...
Hello everyone.
a Ken Wheeler video, in the sense that he's showing things that are pretty to look at, and oh, it looks a little bit like something. This is like ferrocell kind of distortion. So he's going to try to make an end argument that, oh, this is like waves on a pond. And frankly, what he's doing is moving in and out of the focal length of the thing, just showing how the pattern changes. And it's such a distortion and such a forcing something to look some way, just taking advantage of the fact. Okay, so I don't have a quick analogy for it, but it's like photographing anything. You can do it from a perspective and make it look very different than it actually is. They do that with houses, when they're selling real estate. They take these wide angle lens pictures that make everything look huge when, it's really small.
So, many of you will know that light has a strong wave-like character.
All right, so it's not a wave-like character. It just, in certain circumstances, it looks like it, and that's it. And it's only in certain circumstances. So again, it doesn't really have anything to do with anything waving in any real wave-like way. Okay, so you can't show it waving. You can't even imagine it waving in a straight line, for example. So we know photons do this very straight liney thing, that a single photon does not go everywhere. Okay, a single photon is not going here and here and here and here and here. There's no evidence of that. It lands here, or it lands here. So obviously I could send rays out of something, okay? And the rays, you could argue, well, I can just do this to the rays and say the photon, 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 photon. I can do this, photon, 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 photon. I can do that. I can force it to become a wave, but I'm forcing it. It's just a photon, leaves here and goes here, and then another one goes from here to here, and then another one goes from here to here, and another one goes from here to here. Obviously, they're going to create a pattern, but at the same, time interval, there could be a pattern, but it has nothing to do with any real wave. That it's the character of the photon. Again, the photon's traveling from point A to point B in a straight line. I mean, that's what the preponderance of the evidence says. The bulk of the evidence says it goes from here to here in a dead straight line. The bulk of the evidence isn't that a single photon is doing all of this crap. No, individual photons are doing all of this crap. Okay, this is group behavior. This isn't what photons are doing. I mean, you can draw the sun two different ways, right? I mean, this is understood. I mean, you can pretend the sun is radiating sunlight, or you can say rays of sunlight, And one of the theories is right and one of them is wrong. And I'm arguing quite clearly the rays it's rays of energy, not waves of energy. But anyway.
Especially when you look on the microscopic scale. But it's not often that you actually see light waves move almost like the waves that move over the surface of a liquid. So here in these images you can observe the evolution.
So this isn't like he's looking at the light and it's doing all of this stuff. This is a composite of time-lapsed photos where he's moving in and moving out of the pattern. So the pattern's turning on and off and on and off, on and off in different locations, and just creating this is an illusion of a reality. Now it's showing you a phenomenon. It's showing you that at different depths you're getting light from different angles, so you're getting more light from some areas and less light from other areas as you move in and out. And that's what the wave is. The wave is just showing you that, oh, there's more light coming from the outside, and then later there'll be more light coming from the inside. So, but again, this is just like ferrocell nonsense. It's like, try to find it. Try to find God in the picture. That's what it is. It's like, let's try to force it to look like God.
Of light waves after they've passed the apertures of a so-called photon sieve.
All right, he said sieve. It's a sieve, but yeah, okay. So the idea is this simple. So I'm not going to play the whole video, but you put a bunch of holes in and you arrange the holes in progressively. They get progressively smaller as you're going outside, right? So the idea is the small holes spread the light more, right? More diffraction. the small hole means you're more likely to hit the surface. That means you're more likely to be bent, and because you're more likely to be bent, you're more likely to be bent more. So there's light coming off at sharper and sharper angles the smaller the holes are. The big holes, the light goes sort of straight through most of the light, and a little bit of the light gets bent. So as you're going from big holes to small holes, the outside is doing lots of this angle and the inside is doing lots of this, and obviously the combination of that and the combination of this means you'll get a brighter spot. You'll get a place where it will focus. So this is a Fresnel lens kind of idea, and he even states that at first he didn't think this was all that interesting. It's still not that interesting. The color shifts, again, just has to do with each, it can act like a prism in the sense that if you put white light in, then you're going to get different amounts of bending for the different frequencies of light. But so not very interesting. So this is the basic idea. So here's a close-up of what he made. So this is a tiny little thing done with photographic etching and all that kind of stuff to make one of this thing small enough to put under a microscope. So these are little tiny dots and all of that kind of stuff. Blah blah blah. All right, so we'll play some of this.
In other points, the light intensity will actually more or less average out, because some waves might be out of phase with the waves originating from other holes.
Alright, so he stopped playing the animation. So these are all animations. Let's just understand this is taking photographs from different depth, different closenesses to the image. And the image changes because at each depth a different image is being formed.
Create a relatively high intensity, and in other points the light intensity would.
So if you get the right distance from it, you're going to get the most focals you'll get the most light coming from the fringes, from the tiny holes, plus the amount of light you're getting from the bottom hole. And as you go different depths, you're going to bias it towards the center holes producing more light, or the outside ones producing more light. So as you go further away, the outside produces a greater contribution. You go closer, the inside one produces more contribution. Something like that.
Will actually more or less average out, because some waves might be out of phase with the waves originating from other holes.
And again, the reason why phase matters is because the light is really broken. So all the light being bent by the little holes, all of those are just fragments of photons, fragments coming off. And you're really reconstructing a photon by taking fragments from this side and fragments from this side and making a photon. So it's scattered fragments, and then the fragments are reconstructed into a photon. So there is no destructive and constructive interference. There's just fragments and then reconstruction of a photon. The photon can't make it through the small slit. The wavelength and the polarization of the photon is too large to get through the small holes. So only pieces of the photon get through, and then the pieces have to be reconstructed back into the simple pattern of a photon. And it's a simple pattern. It's on, off, on, off, on, off. And so all you have to do is match the phase of the pieces to make a photon. Photons are made out of a Morse code. It's really simple code. So you can make like SOS really easy. Okay, and so all it has to do is make SOS, 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 SOS. And then a photon is remade.
The plan was just to make photon sieves and find out hands-on what they're all about.
Right, so okay, so this is just an explanation of the process of etching the holes and all that stuff. Not terribly interesting. So he did the experiment with just 2 holes, and then 4 holes, and 6 holes, and 18, and 24, and blah, 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 350 and 1,000. And we don't get a whole bunch of that. So that's how small these little tiny things are, the circle with the hole. So just these little tiny things are the actual images of the sieves. But you can see a lot of light's getting through them. So the holes are a substantial part of the sieve. The sieve has a lot of holes in it, obviously, because you can see the light getting through it. But anyway, So, and then this is just an image of the microscope. So this time he doesn't appear to have the sieve on top of 3 layers of glass. So again, his other experiment, for some reason, he had layers of glass underneath, okay, the 2-slit experiment. So when he was doing the 2-slit experiment, he had layers of glass underneath it. So that would be, in my opinion, you'd say, well, why are those layers of glass there? That doesn't sound like a great idea. And so here's his images you get off the microscope. And these are his viewable images. So this is what you would expect from 2 holes, is that you get 2 Newton's rings patterns, right? So it's perfectly consistent with, like I say, particles.
In focus, and if we move the focal plane of the microscope upwards, we observe the...
So as we go further back to get a view of what's happening when you get further away, you're really saying, I don't want to see the little stuff going this way, I'm just going to see the stuff going this way, the stuff that's bent less.
The diffraction pattern caused by the 2 holes. Basically, we just have 2 sources, so you can observe sort of a focal line or plane in between the 2 holes.
Yeah, which isn't really telling you much, right? So that's based on what the distance of the 2 holes were really far apart, if you might have noticed that, right? So they're really far apart, so it's going to make small bars for the distance they are apart, and they're so small that we're not even seeing those. So the actual pattern has little tiny bars in here, but we're not going to see those because they're so tiny. So all we're seeing again is the envelope pattern of the 2-slit experiment.
Anyway, let's quickly move through the different sieves.
So again, as you could see, the focal point wasn't much brighter than all the other points because, too few of the rings are ending up in the same location. So he's creating dots in all kinds of locations, and they're all about equal because there's the same number of rings overlapping. So you just see it. Each sieve, each hole is creating a pattern that's going out, a Newton's ring. And you're just seeing where the Newton's rings converge or are on top of each other, it becomes brighter. So the more rings you can have converge in the same place, the brighter and brighter that place will become. And that's all you're going to see here. So it's not really all that sophisticated. It's just the same principle as the Fresnel lens in the sense that you're just creating angled glass to create a diffraction pattern that always has the same focus from the different locations. And that's all you're doing.
So here's the pattern with 26 holes, so more than 3 times as much as the previous sieve. And here's the diffraction pattern. Now, as you can see...
So they calls it a diffraction pattern, but technically it is an interference pattern in the sense you're saying where do the rings overlap. And where the rings overlap will be bright, where the rings don't overlap will be dark.
There's actually a big improvement in the definition and the brightness of the focal point compared to the surrounding...
Right, so we started to get enough holes, enough small holes from the outside bending light in, and big holes in the center shooting light straight, and those combination now creates overlaps in the center, lots of overlaps in the center. So the more overlaps you have right in the center, the brighter and brighter the center will get.
Area. Still, 26 holes is actually a very limited number, so let's add a few more.
So it's just a focus, and the focus only exists in one area where you have that happen. So where the rings overlap there's a mathematical point where there's a high probability of overlap, and then
here we are
when you go too far,
holes.
too close, no overlap.
So as you can see, the intensity of the focal point actually gets a bit too high for the sensor and the pixels saturate. So if we decrease the sensitivity of the detector, we see that the intensity of the focal point is indeed much higher than the surrounding area.
Well, you could see that anyway. So the fact that the camera couldn't appreciate it fully didn't really matter because you could already appreciate it was much brighter than anything else in the picture. So obviously if you decrease the aperture of the camera, you can see that, yes, you don't see the other light and you still see this light because it was much brighter. So we already knew that, though. You could see that in the other image.
Now the last image is that of the full photon sieve pattern.
So he could go further out and make the dot disappear. So it's just like you're going in, you're finding the focal length of the sieve. So you've made the sieve a certain way, and at a certain location, you'll have a maximum number of overlaps. You still have a lot of wasted light, don't get me wrong. Lots of the light isn't going to be resolvable as anything. So it's a tiny bit of the energy that's going to be the focus. But it's clearly more here than it is here or here. There's like I said, it's just a mathematical circumstance where there's an arc in the space where all of those rings hit the same location and you get a bright spot. So it's a lot like a diffraction gradient in the sense that the diffraction gradient ends up putting dots of light at great distances from each other, and all of the overlaps are all in one place. So all of the diffraction ends up going to one location more than any other location. So you just stack up a bunch of photons in that location and everywhere else is dark because it doesn't have enough pieces going there.
So let's look in a little more detail at what happens near the bigger holes that are closest to the center of the pattern. Now, as I said earlier, it's the edge of the hole that actually diffracts the light.
So there he says the statement, right? It's the edge of the hole that actually diffracts the light. So all of the fringes are being created by the edges. So he's conceding a huge point that just makes wave theory irrational. And it certainly makes Feynman randomness theory irrational. And it certainly makes quantum mechanic nonsense irrational in the sense that it's clearly being caused by a variable, the surface. The surface is the hidden variable. It's right in view. The hidden variable is right in view. If the photon doesn't go near the surface, it doesn't make the pattern. If it does go near the surface, then it does make the pattern. It's that simple. If I make the hole big enough and shoot the laser beam right through the middle and make sure I never go near the edges, I won't get any pattern. None of the photons will quantumly entangle. None of them will superimpose. None of them will do all of this go everywhere in the universe crap. They only do the go everywhere in the universe crap when they go by the surface. So they don't take seriously the logical implications of what they observe to be a truth. He observed it to be a truth that the surfaces are causing the effect, and yet he doesn't think about it and say, what does that mean? Well, that certainly could be called a hidden variable, couldn't it? I mean, that certainly makes the light going through the center different from the light going by the edges, and that they're not doing the same thing. One is doing something completely different than the other, which blows up this notion of Heisenberg bullshit.
And in these bigger holes, you can see how the edge creates interference patterns that are much smaller than the hole itself. And this same phenomenon is actually not...
So you have it, all he's really, I think what he's saying there is you have both patterns, okay? So that's something I've also, pointed out previously in videos, that's part of how they mess up the double slit experiment, is confusing the interior pattern with the exterior pattern. So when you have this, this phenomenon taking place, you have two events. You have the light going out, that's creating the fringes. That'll create, like this light will be matched with this light, theoretically, and create a pattern. Damn, chalk. Now, I'll pause and fix it. Alright, should be fixed. Well enough. And so this pattern is the pattern, these rings are being created out here. But there's also a pattern being created in here, a little tiny one, okay, where you got little tiny, okay, pattern in here. So there's a pattern going inside, and there's a pattern going outside, and they're two different patterns. So that's something to understand.
Observed in the outskirts of the pattern, where the holes are much smaller and act as point sources. And this is also the reason that the small holes get out of focus very quickly, because the light is diffracted under a very wide angle.
It's scattered is what it is. Okay, and it's scattered at lots of angles. Not just at a wide angle. It's scattered at all the angles, but the only ones you're going to view from this position are the ones scattered at a very high angle. So he can't view the ones coming straight through the small holes. He can only view the light coming at a strong angle, but there's clearly a higher percentage of light going at a high angle because the slit is so narrow. The narrower the slit, the more light that's going at the higher angle. The big slits are also producing light at a higher angle, but not as much because not as many photons are going near the surface. The smaller the hole, the more likely the light goes near the surface, right? You can't avoid being closer to the surface if the hole is smaller and smaller and smaller. I mean, so it's all logically understandable. Well, anyway, let's play the end of the video where this is all kind of loop-de-doo. So he's sort of showing it here as waves, but again, you could just show it as, see, this is the deception, right? He just conceded the pattern comes from the surfaces, right? But he's using a drawing where the pattern's coming right through the middle of the slits, right? So he's making a wave coming out of the opening, when he really should have each one of these waves right on the surface. The surfaces are causing the effect, so he should have the little waves on the surfaces, because that's the real cause. So it's inaccurate for that reason. Then it's inaccurate because these aren't waves, okay? There's little pieces of photon. There's straight lines for all the geometry for the path length difference, the wavelength of difference. Where those arcs are just all the mathematical points where the two rays can hit each other, at a wavelength difference. That is back in phase. Back in ... instead of ... So all you're doing is putting them at the proper distance from each other by traveling the proper distance. So you have a full wavelength of difference in the vector, the path. And when you have a full wavelength difference in the path, you can reconstruct a photon there. Where there's not a full wavelength, a half wavelength, you'll have ... You won't have a photon. You won't have the right message. So they should be just straight lines from these points, and again, it would be on a curved surface. The math will never be on this flat plane. The math has got a real distance in it, and that distance always stays the same. So it's just sort of a distortion to say that the geometry goes to this flat plane, because the geometry doesn't go to the flat plane. All right, so play the rest.
The focal plane is traveling along the path of the photons. And so the images also represent a time-resolved record of the development of the light waves.
So he's saying it's doing something. So again, this is just a time lapse of moving in and changing the image. That is changing where the light sources are more dominant. And so it looks like something, but it isn't like what it looks like. There's no structural waves built into any of this stuff.
And now you see how light is behaving very much similar to the waves on a surface of a liquid.
So again, it really isn't. There's no part of it that's actually doing that. It's just the fact that you're changing the depth, so you're changing the places that the light, the geometry is a wavelength of difference. So as you're going deeper in and out, you're just changing the place the light is diffracting to where the wavelength differences match. And so it looks like something, but it isn't real. It's not a real cone. It's not a real, these aren't real places in any one space where something is waving. So again, this is sort of like ferrocell deception. I can make it look like something, but it's just an abstraction. I'm distorting your viewpoint, changing your viewpoint, manipulating your viewpoint to create the illusion of something. And this isn't, sorry, but it's not my opinion. It's very good technical science in terms of the hardware and the fact that he did these experiments well, but it's really bad science in terms of what he's forcing it to look like. So the dominance of that center one just has to do with that's where one of the big holes are. So that just happens to be where his microscope is, over that hole. So that ring is dominant, and everything else is just magnifying it. So the more light that can go to that location that that one's creating, that's the one that's the most likely to be visible, because you're getting the most light through that hole. The most fragments, the most pieces are coming from that center hole, the one that happens to be under the microscope. So one of those big holes just happens to be the one under the microscope, and anything that matches that, anything that has the same path length difference, will just magnify the strength of that image. And that's why it looks like a wave going out. But there is no wave going out. It's not real. It's not like water. It's not in any way the same phenomenon. It's not. It doesn't have any mechanical similarity at all. But me saying that to you, just, I don't know if it means anything. But, 272 thumbs up, 0 thumbs down. And it really isn't very good science. It certainly isn't good science in the interpretation end. Okay, the production end is good, but the presentation of the experiment is poor. All right. So enough of video and such. Anyway, is there any point, Gary? Keep asking yourself that, and then keep answering with endeavor to persevere. Because what the hell is it? Doesn't matter whether there's a point or not. I can only fight for right. That's all I can do is, run into the mouth of the enemy and see if I can cause it some damage. So till the next time and such. This has been a DraftScience video presentation and such.